Okay, lesson 5-3, graphing radical. Radical means like square root, cube root, those kinds of things, functions. And so what you see on this opening slide right here is your square root of x graph is just this basic one right here. I put a couple points on there to kind of point out, if I do a square root of 1, it's 1. If I do a square root of 4, it's 2. So if you think about where those points would lie. And then down on the bottom there is showing you your normal transformations still apply here. So if I'm going to do an x minus 2, remember when you have that minus 2 on the x, that takes that yellow graph right there, and it's just going to shift it all to the right 2 units. So it should be the exact same graph, just translated, slid to the right 2 units. Same sort of thing over here with the cubed root. So if you see the original cubed root of x, so that would be the one that goes through 0, 0. Kind of pointed out these other couple of points here as well, like this 8, 2, or -8, -2. Cube root of -8 is -2. And in this case, if you put a +2 onto that same thing, then this one is going to move it 2 to the left. So there's your 2 to the left. Should be the exact same graph, just slid over to the left 2 units. Continuing from there, well, what would these look like? So if you have your first graph over here, and sometimes I still like to even put the parent graph on there, the plane, what if it was a square root of x? Kind of gives you a little bit of, orientation to the, so that would look like that, right? And then in this case, if you add to it your +3, which would be 3 to the left, so this starting point here moved over here, 3 to the left, and then a stretch factor of 2. So if I went over 1 and this goes up this much, when I go over 1 here, it should go up twice that much. So it's going to be like it's a steeper looking graph, but still that same shape. Stretched it vertically. The second one over here, well, what would happen there? Or I could put that on the same, if I put this one in pink over the top here. So this -1 would be 1 to the right. So that would be over here, and then still the stretch factor of 3. So it should look just like this green one. I don't think it's not quite the same steepness as the green one. That looks like maybe a little better. So that those two would almost be like they were parallel. Well, what all happens in this one, there's one extra little trick that you have to take care of here. And that is if you want to see this horizontal stretch here, what that has to do, you have to factor it out. So inside of here, I think 7 times 0.5 is 3.5. And then this +2 sitting outside of there. So our parent graph would be the just square root of x. And so when you put this blue one on here, 0.5 to the right, so if that's 1, 0.5 to the right, then 2 up, so take this and move it up 2. And then this horizontal, remember this has an inverse relationship because it's inside here. So then where you would normally think it would stretch it, it actually has, or it stretches it horizontally, which makes it look like it compresses it. So it horizontally happens 7 times faster. So maybe I should have put that, if that was my normal graph, so that where this went up 1 and 1, this would have to go over 7 in order to get up 1. But the factoring this out, and then it's an inverse relationship from, as opposed to like the vertical stretch if it was outside here in front. Well, what if they give you a graph and they want you to write the equation? Well, let's go over here. So this point right here, if that's my starting point, hopefully you recognize this as the parent graph would be the square root of x. but then 5 to the left would be a plus 5, and this 4 down would be outside of here, 4 down. But then let's see if there's some sort of a stretch factor on that. So if you have this point, and then you take one of these other 2 points, or there's a couple different ways you could do this. If this goes from -5 over to -1, that's over 4. Normally, if you think about this, if you were at 0 and you went over to 4, it would go up 2, right? So if this one's over 4 and it goes up 2, it must not have a stretch factor, but we can also solve for it algebraically to check it. So let's just take this point. You could use this one also, and we'll put it in here. Like the -1 is our x. The -2 here is my y. And then the only variable left is the stretch factor a to solve. So in order to solve this, add that 4 over to this side. -2 plus 4 would give me 2. And then 5 plus -1 would be 4. Square rooted is 2. And if you divide by that 2, you're going to get your 1. So this a right here is 1. And if you're multiplying by 1, you could leave it out, which means my equation is right there without that stretch factor. We'll come over to this second one, and hopefully you recognize this one as a cube root of x graph. And so if that's a cube root of x graph, where's my locator point on the cube graph? Hopefully you would agree it's this point right here. It's not given, but that was at 0, -2. So that we get these next 2 points out here that are symmetrical on each side. 2 to the left, 2 to the right. And so if that's at 0, -2, left and right, there's nothing in here shifted, but it's been moved down 2. So from that, so far, down 2 shift. But now check for a stretch factor. So you can use any one of those other 4 points that we haven't already used. We've only used this point. Once you've used it, then you can't use that again. But now pick one of the other ones that you like the numbers on. I'm going to stay over here to the positives. I'm kind of liking this 6, 1. The 6 is your x. The 1 is your y. And then we'll solve this. So if we solve it, add that 2 over. Divide by that square root of 6. Remember that sometimes they don't like square roots in the denominator, so to rationalize the denominator, they call it, getting a plain integer number down there. So we'd have 3 square root of 6 all over 6. And those two are going to simplify to make a 1 and a 2. So square root of 6 over 2 would be the answer that you would put right here in place of this a to get your final answer. But let's just check one of the other points and see that we get the same answer. So I don't know, I don't like working with the negatives, but we'll take this one this time. So if our graph was 2 to the left, so that would be x plus 2 under there. And oh, wait a minute, I'm like using the wrong equation. Back up here. My equation, then I want to just plug the -2, 4 into this equation for the x and y. So my y was -4. My stretch factor, we're trying to check again here. A cube root of x and then a -2 out here. So I'm putting the -2 under here for x. Stretch factor Add the 2, that gives me a -2. Divided by this cube root of -2. And that's kind of gross. I think I messed something up someplace else where I did not use a cube root down here when I was doing this part of the problem. I forgot it right here. Rats. Back to the drawing board. So let's go all the way back. That solved to give me the wrong answer then because I left out that cube root. Get all this out of here. All right, let's put that cube root back in here where it was supposed to be. So again, added 2 over to this side was 3. And divide by the cube root is 6. Now, in order to get that into a plain number, I need 2 more 6's here. Could change it into rational exponents and work with fraction exponents as well there. So then this down here becomes 6, and up here I've got the 3 and a cube root of 6 squared. So this 3 and this 6 would reduce or simplify down. Cube root of, if you want to leave it as 6 squared, if you want to type 36, and then over a 2 there. So something equivalent to that form. Now remember, that was my A there. So this whole thing just went right in front of here to get the equation for that graph. Well, we've got Sasha here standing on a cliff or hiking on a path, if you will. And as you walk along the path, it's on a cliff overlooking the ocean or a long distance away anyway. And maybe it's just hiking through the hills. And based on the distance that they are above ground, the height, elevation, that determines how far horizontally and they can see. So this problem says if Sasha's brother is at an elevation of 8 on this path up to 48 feet above sea level, whatever, how far can they see? So if you put an 8 in here, because the elevation, that's the height. So you're just plugging it in there. So whatever that comes out to. And then some parts of the path get as high as 48. So then on that one. And so that would be the range of the distances that can be seen when you're along that trail. If you wanted to work those out, this one I think is 72. Half of 48 is a 24, added onto the 48, 1.5 of the 48 is 72. And 1.5 of the 8's, half of the 8's a 4, added onto the 8 would be like a 12. And then remember, square root of 12 is 4 times 3. And so in simplified form, the 4 square rooted is a 2 and the 3 is left inside. And then on the 72, that's 36 times 2, and the square root of 36 is a 6. So the range of distances that Sasha's brother can see are from 2 square root of 3. I don't know that we were given units here. Feet, miles. Well, we'll just say units. I think that's everything then in 3-1.